All right, everybody. Welcome to the end of the second week. Time flies, right? All right, any questions at this point? Hold on, letting in a couple people. Everybody, I sent a message. I moved the exam from next Tuesday to the following Thursday. I'm just looking at the schedule. It's going to be that way for the first one. It's always is. We try to anticipate it to be on Tuesday, but given the amount of information we give you in the first couple of weeks, it's I always end up moving it. But the other exams should be pretty much set. Anyway, any question about where to get the information, where to get your textbook, where all the assignments are and so forth? No surprises, right? All right, well, let me continue with chapter 2, slide 18 is where we left off. And we were talking about rounding the numbers up. Okay, now, why are we doing this? Well, here's the thing. When we do calculations, which we're going to do quite a bit in the next chapter, and down the road when we do calculations for chemical calculations, the emphasis, the main point of all this is that you don't want to present your data more accurate than it really is. Okay, yes, and we understand that you type in numbers in your calculator and you can end up with 15 digits. What that doesn't mean that is the correct answer, because you are limited. Your answer should be no more accurate than the least accurate numbers that you did with respect to whatever mathematical function you did. Okay, and we're going to talk about this here in a second. We've been talking about sig figs, significant figures. Now, there's a different thing with respect to multiplying, dividing, and sig figs, and there's a different thing with respect to adding and subtracting. Okay, when we multiply and divide numbers, we look at the significant figures of the two numbers that we're doing multiplying or dividing. When we add and subtract, we're not looking at sig figs, we are looking at decimal places, and we'll have more about that here in a second. The main point of the two is that you in either case, the answer should be no more accurate than the least accurate number that you utilize. Okay, so a lot of times you get a question that says, present your data in the correct number of significant figures. What I want you to do when you see that is think this. First of all, number one, what am I doing mathematically? If I'm multiplying or dividing, then I got to think significant figures. Okay, but if I'm adding or subtracting, I have to think decimal places. All right. Now, once we know that, what we do is we have to round the number up or down, depending, not down, but we have to round the number and truncate it. And we use the rounding rule. So we look at the number that we need to do the rounding at, and that number either is going to stay the same or it's going to go up. We're going to round it up to the next number. And it's all dependent on the number next to it. We don't care, and I overemphasize this, we don't care about the number down the road, 4 or 5 numbers down. It has nothing to do with the rounding. We only care about the immediate number next to the number that we have to round. Okay, and if that neighbor is less than 5, then that number that we're going to work with stays the same. So in that example we did here, 5.4, we are looking at the neighbor, which is 4. Okay. And that 4 is less than 5. Therefore, that number 5 remains the 5. And that's how we present the data as 5. If the number is 5.5, for example, and we want to round it off to the first digit, then we look at the neighbor, which is 5. And 5 is greater and equal to 5 itself. Therefore, that number we're going to round becomes 6. Okay. Now, the key part about all this is the magnitude. Okay. I can't overemphasize this also, because what tends to happen sometimes when we're rounding numbers off, that students tend to eliminate numbers and you change the magnitude. Now, what do I mean by this? Okay, let's look at the number down at the bottom, 5,400. The problem says to round it off, round it to 1 sig fig. All right, so starting from the left, moving to the right, the 1 sig fig position is the 5. So it is the 5 that either is going to remain 5 or it's going to be pushed up to 6. And we determine that by the rounding rules we just talked about. We look at the neighbor, okay? And the neighbor's 4. The neighbor's 4, which means it's less than 5. Therefore, the 5 that we're going to round remains 5. And we present it as 5,000. So the 4 gets converted to 0 and the zeros stay there. Okay, now what happens is students at times drop the 4, the 0, and the 0, and they end up with 5. And it doesn't kind of click that you have changed the magnitude. So let me ask you this. The best way I can tell you about the magnitude is put the dollar symbol in front. Okay, by dropping the 4 and the 2 zeros, having you gone from $5,000 to $5. Big difference, right? Okay, you change the magnitude by dropping the zeros. So remember this, when there are numbers, and I'm going to generically just call them X and decimal point, and there are more numbers, and I need to round it off, anywhere, any of these, okay, the first 3 X's, that means that the X's after the decimal point get dropped. They're gone. Okay, but any numbers before the decimal point, like the 4 here, we convert to 0. We don't drop them, because if we drop them, we change the magnitude. All right, change the magnitude. Now you might also say, well, what happens? What if I don't drop them? What if I add zeros? So instead of 5,000, you present it as 0.0. But what has happened now by adding a point in 0? How many sig figs do we have now for 5,000.0?
5.
You got 5, exactly. So we changed the sig figs. So that's like not it would be incorrect. Why is it incorrect? Because the question said, no, we want just 1 sig fig. Okay. If the question said put it in 5 sig figs, then you'd be correct. All right. So don't change the magnitude of your answer. All right, so here, in this case, they're asking you to round the number. So you did something mathematically and you ended up with this answer in your calculator. But based on the digits that you did and the mathematical function that you did, which will be clear hopefully here in a bit, you have to round it to 3 sig figs, okay? So what we got to do is to identify the 3 sig fig position, and you starting from the left, working your way to the right, you identified that the 3 is this 3 sig fig position. So the 1, the 8, and the 3 gives you 3 significant figures. That means the 7 and the 4 are going to be dropped here. Why? Because it's after the decimal point, right? Now the question is that 3 got to go to a 4 or does it stay in the 3? Well, we look at the neighbor in the rounding rules. That's set at 7. We don't care about the 4. We just care about the immediate neighbor. 7 is greater than or equal to 5. Therefore, 4, the 3 becomes the 4, excuse me. Okay. And so now that's the answer that you will present with the correct number of sig figs. Okay. Yes, I understand your number 1.8374 seems more accurate. Okay, because you got more digits, more decimal places, but it's incorrect because whatever you did to measure to get that number only had 3 sig figs at the most. You can't be more accurate than that. Okay. All right, the second one. You got 7,162.32. All right. Now, with respect to the first one, you can see here that when the 7 and the 4, if you add zeros to the 7 and 4, you, like I talked about, you increase the number of sig figs, so that you won't want to do that. You didn't change the. Let me restate that. let's say the 7 and the 4, instead of dropping them, you converted them to zeros. Well, what in effect have you done? You increase the number of sig figs, right? Because those zeros count. Okay, so that would be incorrect, but you didn't change the magnitude. All you did was change the sig figs. Over here, you have to be aware, you got numbers in front of the sig fig, in front of the decimal point. And the 6 is where you need to round up or round down or leave alone, I should say. The question is the 2, okay, is part of the magnitude of your number. You're at 7,000, okay? You're in the magnitude of 7,000. If you drop that 2, then you end up with $716. Totally different magnitude, right? By factor of 10. Okay, so you got to be aware of that when you do that. Don't lose the magnitude. Right. In this scenario, we need to identify the 3 sig fig position. Remember, the zeros in front are leading zeros, so are not considered significant figures. So we start counting from the 1 and move to the right. And the 1 after the 3 is the 3 sig fig position. Okay. Now we look at the neighbor. Neighbor is 1. All right. So that means that the 3 sig fig 1, that position stays 1. So our answer is 0.00131. And don't forget your units, millimeters. Okay. Here, 3 sig fig position is the 9. Okay. Notice that the 2 and the 5 are before the decimal point, and so you want to convert those to 0 because you are in the magnitude of 24,000. Right. So 9 remains 9 because that 2 is less than 5. So your answer with respect to the correct sig figs is 24,900. And the key points is this: first of all, drop the numbers after the decimal point. And unless, for example, you might say, well, wait a minute, I'm a little bit confused here. Okay, let's go back for a second. Because the question says 3 sig fig position, but what if it was 1, 2, 3, 4, 5 sig fig position? Then that would be the 3, wouldn't it? Right? And so that means we look at the 2 we can drop. So if it was 5 sig figs for this one, then the answer would be 7162.3, right? If the question was 5 sig fig position. I got a tech support question to Canvas. Tell them, why are you messing with my pen? I haven't got the response yet. All right, so be aware of the problem. Why sometimes in this case, because we're only doing 3 sig figs, we drop the 3 and 2, but it could be a scenario where you got to keep a number after the decimal point. It all depends on the question. Okay. All right. Now, so as I mentioned earlier, when we are multiplying and dividing, we have to be aware of the number of sig figs. So our answer should be no more sig figs than the number that has the least number of sig figs. When it comes to adding and subtracting, don't worry about sig figs because there's no relationship. Okay, we worry about decimal places. Now I'll explain that here in a second. So your answer should have the same number of decimal places as that number that has the least number of decimal places. Let's take a look at this: 13.5478. Okay, and we're gonna subtract, but this is true if this is plus. Now, of those 2 numbers, can you see which one is the least accurate? Which one do you think is the least accurate? The 13 or the 11? Okay, what we got here? 4 answers. All right. Yeah, the 11, exactly. The 13 wouldn't be the least accurate. The 13 has 4 decimal places after. Okay. 4 decimal places. Whereas the 11.20 has two decimal places. And so think about this, if this is a measurement, the 13.5478, maybe they use a laser to get that measurement. It got it very accurate to the fourth decimal place. And the 11.20, maybe they just use a regular ruler to get that 100 place with a lot more increments, enough increments for the 100 place. So the 11.20 is the least accurate, which means that when we present the answer, it should be no more accurate than the number with the least decimal places. So you do the math, be it addition or subtraction, do the full number. Don't round off any numbers until you're done with the mathematics. So you see, as subtracted, you get 2.3478 as your answer with all the digits. This has two decimal places, so your answer should be truncated at the second decimal place, the 100 place. So at this point, you identify it, right? That's the 4. You look at the neighbor like we've been doing, it's a 7, so that 4 becomes a 5, okay? And so now you see here, we got 2 DP decimal places. And this one has 2 DP decimal places, whereas this one had 4 decimal places. So you can see we've maintained our accuracy because our least accurate number is the one with the 2 decimal places. Okay, has nothing to do with sig figs. Who can tell me how many sig figs does 2.35 have? 3, exactly. All right. There's 3 sig figs here. Okay. How many decimal places does the how many sig figs does 11.20 have? 4, exactly. 4 sig figs. And finally, how many sig figs does the 13.5478 have? Isn't that 6? Okay, exactly. So you can see that when it comes to adding and subtracting, that sig figs are not a factor. Okay, because your correct answer has 3 sig figs. When you multiply and divide, yes, sig figs are a factor. Okay, but not when you add and subtract. So you add and subtract, think decimal places. When you multiply and divide, think significant figures. Okay, and if you ask the question to present your data with the correct number of significant figures, which I know some of the questions have that, think about what you're doing mathematically. Okay, if you're doing mathematically, adding it, multiplying, dividing, then think about sig figs. If you're adding and subtracting, think about decimal places to present your data in the correct numbers of significant digits. Okay. Focus on decimal places. This is just a reminder to help you out as far as the magnitude of numbers and where you're at, just a refresher, 100 place, 1,000 place, etc. Okay, multiplying and division. The final answer has the same number of sig figs as the least sig fig. Okay, let's take these two. Now, how many sig figs does 3.546 have? Okay, 4, exactly. So we got 4 sig figs. All right, now how many does 1.4 have? Exactly, 2 sig figs. Okay, since we are multiplying here, our answer should have no more than 2 sig figs. Okay, nothing to do with decimal places, remember. Okay, don't mix and match the two things I just talked about. All right, if you add and subtract, don't throw in sig figs, you just throw in decimal places. If you multiply and divide, don't throw in decimal places, think sig figs. So our answer should have no more than 2 sig figs, because the 1.4 is the least accurate number. It's the least accurate number. So you do the math and you whatever the calculator gives you, you put that number out there, okay? Which if you multiply that, you get 4.9644. And since our answer should have no more than 2 sig figs, we find the 2 sig fig position starting from left to right, and that's the 9. And we look at the neighbor like we've been doing to determine whether that 9 stays at 9 or goes up. And the neighbor is 6, so that means that 9 goes up to 10. So we carry over the 1. So our answer is 5.0 with the correct number of 2 sig figs. This number is not more accurate than the least accurate number that you use in the mathematics here. Okay. Yes, the number here has a lot more decimal places, but that doesn't make it correct. Okay, because you're limited by your least accurate number, which is the 1.4. All right, so multiply, divide, focus on the sig figs. Add and subtract, focus on decimal places. The other aspect is this: when you do multiply and divide, you know that when you add and subtract with respect to units, you have to have common units, right? I mean, if I was 10 meters plus 10 centimeters, could I add that together? I can't. No, I can't, because I need to convert either the centimeters to meters or the meters to centimeters before I can add them up, right? Well, and the same is true of subtracting. And so if this was 10 liters and you got to add 10 centimeters, well, I can't do that. I got totally different units. I can't. I got volume and length here. But if I'm multiplying and dividing, the units really don't make a difference. You know, because remember that density? The density was grams over volume, milliliters. That was the units of our answer, grams over milliliters. When we multiply, don't forget your units. Let me clear this up. It's getting a little bit messy here. You know, we got 3.546 meters times 1.4 meters. Obviously, meters times meters is meters squared. And if we were to multiply that with meters again, we're going to get meters cubed. And again, meters to the 4th, meters to the 5th, okay? So don't forget your units. So this square meters. All right. Now, which brings us to scientific notation. Scientific notation is a method by which we can display and write, excuse me, something's making me sneeze. Display and write very large numbers or very small numbers, like the example here. On top, we got a very large number. Bottom, we have a very small number. Okay, a number much less than 1, a very small. And we use scientific notation so we can display, instead of writing it out longhand, we write it in the shorthand method. For example, if we take this number here, 93 million, it's approximately the distance from the Earth to the Sun. Okay, we want to write this in scientific notation. Now, in writing anything in scientific notation, the point number 1 that you must make is to determine how many sig figs you have, because your answer should also continue with writing the correct number of significant digits. Okay, and so 93 million has 2 sig figs. So you got to make sure that your answer has 2 sig figs. Now the format is as follows. What we do is we look at where the decimal point would be, which is obviously in the last 0. And this number being much greater than 1, we start from the right and count the decimal places to the left until we stop at the last integer in that number. And so starting here, we go 1, 2, 3, 4, 5, 6, and 7 right before that 9. Okay, so that's where the decimal point is, 9.3. Okay, and then it's times 10 to the exponent 7, because that is the number of decimal places it came across. That is no different if I were to write it longhand to say 9.3 times 10 times 10, etc. So I got 7 tens. That's this number up here. Okay. And so this is the correct format for scientific notation. We got 9.3 times 10 to the 7th power, where 7 represents how many decimal places you moved. Notice the the 7 is a positive number, okay, because you can't have negative numbers. It's a positive number that tells you it's a number greater than 1. Obviously, 93 million is a number greater than 1, okay? Now, that is the correct format where we always have an integer point, then the decimal point, you may be there, and then whatever numbers follow, okay? You might be tempted to write it as 93 times 10 to the 6th. Yes, that is the same number for 93 million, but it is not in the correct scientific notation format. The format is integer, and if there is a decimal point, and then whatever number you need to do. This number up here will always show you, and you always write that with the correct number of sig figs that you need to utilize, okay? And in fact, there will be times when you have a number and you're not sure how to write it in the correct number of sig figs whenever it becomes ambiguous. And when you hit that number, if you ever have a number like that, convert it to scientific notation, because there's no question when you put it in scientific notation, this up here always displays the correct number of sig figs, okay? So when in doubt, convert it to scientific notation, and we're going to have some examples of how to do that. All right, now with respect to small numbers, okay, very small numbers, notice this number here. You got 0.000, so on and so forth, 17. Okay, point number 1, 2 sig figs. We're gonna always keep track of that, sig figs. We got 2 sig figs, so we are going to have 2 sig figs. I can very quickly, I'm gonna start, here's my decimal point. Instead of going from right to left, in this case, because it's a number less than 1, I'm going from left to right, okay? On your camera, I don't know, it's right to left, but from left to right. So I start here and I count the position, and I keep going, counting to the position until I stop after the first integer that I encounter, which is the 1, okay? And so it is 1.7 times 10. Now, this time, the exponent 10 represents how many decimal places I moved in, but I have a negative this time, okay? Because this is a number less than 1. So now, this number here in scientific notation is presented as 1.7 times 10 to the negative 10, okay? And this is nothing more than if I take 1.7 and I divide by 10 times 10 times 10, etc. So I got 10 of them, okay? That's just another way of writing that number, the negative. Okay. All right, so question here is asking you to take these numbers and convert them to scientific notation. So step number 1, I always give you a systematic approach. Eventually, when you are comfortable, you can create your own approach and how you want to attack the problem. But step number 1 is determine the number of sig figs, because your answer should also have the same number of sig figs. So number 1 has, how many sig figs does number 1 have? Anybody? What do you think? How many sig figs? 548.005. What do we got there? We got 6 exactly. Okay, and said we're going to end up with 5 sig figs at the end, so we can't drop any numbers. Step number 2, it is a number much greater than 1. And so I'm going to have a positive exponent. Okay, so I'm going from right, find my decimal point, and then I move here from right to left. So I go 1 and 2, I keep going until I find the last integer and I stop right in front. So that becomes 5.480005 times 10 to the second power. Okay. All right. The next one, similar scenario, the number greater than 1, so my exponent is going to be positive. Second of all, I have 3 sig figs, and I know the format is going to be 6.81 because that's just the format of scientific notation, so I can write that quickly with my 3 sig figs. Okay, and I know it's going to be times 10 to some exponent. Well, to determine that exponent, find where the decimal point is, and just count the decimal places until I stop in front of the 6. And I got 3, 6, and 7. Okay. And of course, my units there. Okay, so 6.81 times 10 to the 7th meters. That is that number 2, written in scientific notation. All right, the next one, determine I got 3 sig figs, right? Because the first 3 are not considered significant, all right? But the second 2 after the 4 are. If you forget, ask the questions. For these 2 zeros after the 4, is there an integer in front of them? Yes. Is there a decimal point in that number? Yes. So those zeros count. All right. Find the decimal point. In this case, it's a number less than 1, so I'm going from left to right. So I got 1, 2, 3, and 4. Find the last integer, the first integer, and stop right afterwards. So 4.00 times 10 to what I say, 1, 2, 3, and 4 times 10. Don't forget this, -4. Okay. Because it's a number, it's a decimal number, it's a number less than 1. And then the 2000, you got 1 significant figure. I know I'm going to have 2 by itself times 10 to the 3rd. Okay. And that is scientific notation for 2000. Now ask yourself a question. What if you're given the number 2000 and you're asked to write it with 2 sig figs? Can I do that long-handed? Can I write the number 2000 with 2 significant figures long-handed? Kind of ambiguous, right? I can't put a decimal point in there. Why? Because then if I put a decimal point in the 2000, now the 3's count, and now I'm 4 sig figs. Okay. And this is an example of what I mean by putting it in scientific notation, because there's no ambiguity there. So this is the number with 1 sig fig, 2000. If I want to write it with 2 sig figs, guess what? I take my 2.0 and just add a 0.0. 2 sig figs. If it wants 5 sig figs, guess what? 1, 2, 3, and 4 times 10 to the 3rd. 5 sig figs. All these numbers are 2000. They are just written with different number of significant figures. And we can do that because we put it in scientific notation, because we know that these zeros are considered significant. They're in scientific notation, makes them significant. Okay. And sometimes, people, you can be asked questions, write 1,000 with 2 sig figs. No, I can't, I can't do it like that. I gotta convert that to scientific notation. And And that is the number 1000 written with 2 sig figs. Okay, so that's what I mean by when in doubt, and if you're not 100% sure how to write it longhand with the correct number of sig figs, simply convert it to scientific notation. There's no ambiguity there. Okay. All right, because scientific notation always shows your sig figs. Now, once we know about sig figs and how to, scientific notation, how do we put it in the calculator to do calculations? Well, there are three, to my knowledge, there may be new buttons out there. There are 3 types of buttons that I've seen out there that the calculators, they represent the scientific notation format or function in the calculator. The one here, the white, this is the calculator for Windows. Now, I don't have a Apple, so I don't know about the calculator for Apple. So you might want to check that. So there's a button called labeled here, circled in red, called EXP. That button will push you into the scientific notation function. Okay. Now there's some old calculators that have the function button EE. I've circled that one there. That is the function for scientific notation for some calculators. And the newer ones have the button that is labeled 10x, little x, 10 to the x. Okay. That is a scientific notation for that calculator. Not to be confused with the button that's labeled 10 to the x. That is not, that is not the scientific notation button. Okay. Totally different function there. So if you're not 100% sure, shoot me a image of your calculator or look at your manual. Okay, and determine where is the function for that. Another button you need to determine is it's a toggle button that puts you into positive or negative. For the Windows calculator, it's this one right there. It's a +/-. So sometimes you can add a negative number. So you hit that. This calculator has this button right here, plus, and then some symbol negative. That's the toggle. And then the other calculator, new ones, that button is a toggle to go from positive to negative. Okay. Let me see what else. That's about it. Now, the other aspect about your calculator is these calculators have this function, primary function, it's up front. Your calculator depends, it could be a secondary function. So you may have to push the second button and then maybe scientific notation, like in this one in the middle, could be the secondary function, in this case, like in gold color. So to access that, you got to hit the second one. So that's what I mean. Take a look. And all of these have, like these two on the left have a second function for the button. That means you got to hit the secondary button to access it. So be familiar with that, because we'll be using these scientific notation to do calculations with big, humongous numbers. All right. So let me go back. And so what happens in this case here, if I want to type in 2.39 times 10 to the -9, the way you do, and we're going to use the double E button, if that's the calculator, we type in 2.39 and then we hit the E button and then we hit the 9. Okay. What I'm going to do is share the calculator, my calculator, clear it up a little bit, and input that number. And the number we were going to input is 2.39. Come on, times 10 to the 9th power. Okay. All right. So to do that, I'm going to use the Windows calculator. I type in, this is true for any of the calculators, you type in the 2.39, so 2.39. Okay. Now, if this was a negative number, I would use that toggle button to give me back the, see, notice when I click it, I get positive, negative, positive, negative. So if it was the exponent, I would use, it was a negative exponent, that's the button I would use. Now, in this case, I click the EXP button. Okay, now the Windows calculator, to tell you that you're into scientific notation, puts an E letter after the number you put in, the 2.39. Okay, then it puts a plus. At this time, you type in the exponent. And so the calculator presents that number, 2.39E times 10 to the 9th. Okay. The thing about that is this. This is not the correct format. That is the format for the calculator. If that was your answer, you would need to take that and convert it to 2.39 times 10 to the 9th power, the correct format. Okay. Sometimes even that number depends on your calculator, would be presented as 2.39 and then put the 9 on top of there as a superscript. That is also not the scientific notation. That is the format for whatever calculator you have. So you would need to take that and convert it to scientific notation. Okay. Now at this time, you can multiply, divide, do whatever you want to do with that number. Okay. And we're going to do some examples of that. Let me go back. All right. Sometimes you might be tempted, unless your button has X 10 to the X, okay, do not, type in the number 2.39 and then hit the times table and then hit that function 10 to the X. That is not scientific notation, okay? You got to have a button. It's one of those three choices. That's what they're telling you here. Don't do that. It's a totally different number. All right, so that's that picture there. So you do need your calculator. Okay, now let's type in this number. The number is, in fact, I'm going to share my calculator with you again in a minute, so you may want to write this number down. It is 2.84 times 10 to the 23rd divided by 7.29 times 10 to the 12th. Okay, so right now, as it stands, I'm doing a division. So how many sig figs should our answer have? Exactly 3. Both of these numbers, the numerator and the denominator, have 3 significant digits. Therefore, our answer should have no more than 3 sig figs. Okay. All right. So that's the number. Now I'm going to share the calculator. Let me clear it. All right. So the first one was 2.84. Oh, went too many. My mouse is not cooperating. 2.84. I hit the scientific notation button. Oh, let's clear that up again. 2.84. Then the EXP button. Okay. And then 23. If this was a negative exponent, then I can just simply toggle it. See that? That represents 2.84 times 10 to the negative 23rd. But it's a positive. Now I'm going to divide. So I divide like I normally would. So I hit the divide and then input the next number, 7.24 exponent to the 12th. Okay. Notice the number I have here, 3.922651933, blah, 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 e to the 10th power. Okay. Sometimes your calculator might present that number in longhand. You may have some calculators have a F-E button, and that's a toggle to go from engineering, which is scientific notation, back to floating point. number, so this is the floating point number written in longhand, or I can go back to scientific notation and toggle that button. Your calculator may have a ENG button, engineer, that kicks it back into scientific notation. Now, let's take this number and bring it back to the slide. Okay, and the number we obtained was that big giant number. Okay. Now, we already demonstrated that E function here, that is the format for the calculator. That is not the correct format for scientific notation. So I would convert that E to the symbol, the times symbol, and then 10 times 10. And then I will use the, what they call the caret symbol, that's a shift 6. That shows that the next number will be superscript, okay? Now, it's not necessary to put the plus 10 because in mathematics, if there's no symbol in front of that number, it's assumed to be positive. So that will represent that number, 3.9999 times 10 to the 10 power, okay? Now, obviously, too many sig figs, right? And so we already determined we have 3 sig figs. So starting from the far left and moving to the right, the first 2 is where we truncate. We look at the neighbor's 2, which tells you that that 2 will remain a 2. So we erase all the other. And so now that's the format that we will present that number, the answer for that mathematical function that we just did. 3.92 times 10 to the 10th power is what our answer is. Okay. Point 2. All right. All right. Any questions about that? Now, sometimes this was about the second function in case your scientific notation is a secondary function in a calculator. Make sure you hit the second button. And then also sometimes there's a question. No, the question is this, Thomas has the question. So in scientific notation, we're allowed the maximum of 1 integer. No, there's always at the minimum, always going to be 1 integer in your answer. Okay, always. Right there, like 3 in front of the decimal point. If we need to go one integer, then that number 3.92 will be rounded to 4. 4 times 10 to the 10th. Okay. So there's always going to be an integer up front. Then, depending on your sig figs, there'll be followed by a decimal point, and then whatever digits you need to get the correct number of sig figs. Okay, did that answer the question?
Yes, Professor, but so we allowed to have. So can we write it in 39.2 to the power of 9?
Oh, no, no,
10
no.
to the...
Oh, I see what you're saying. No, let's go back to back here. Where'd it go? Okay, remember this one here? 9.3 times 10 to the 7. That is the correct format. In other words, there's always going to be a number X, and then you may have a decimal point, you may not, and then whatever follows other numbers. Okay. So at the minimum, you're always going to, and then times 10 to, maybe I should write it more like, let me do it this way. What you're asking is here. Like that example here, notice here,
Uh-huh.
93 times 10 to the 6. This is not the correct format, okay? The correct format is you're always gonna have an integer up front. Then, if necessary, you will have a decimal point and then whatever numbers follow, or zeros, or whatever numbers you need to give you the correct decimal, the correct number of sig figs. Okay, so you always want to keep it single. So if there was one sig fig digit, then this would be 9.0 times 10 to the 7. Yeah. If I needed one sig fig, right? So there's always going to be one digit, but not like this. Did that answer your question?
Yes, I
So,
think I understand it now. Thank you.
yeah, there's always just one number, one integer at the minimum. That is the minimum you can have. But if you have significant digits to put in there, then you're going to have that one number followed by the decimal point, and then whatever digits you need, be it zeros or be it whatever numbers. Okay,
Thank you.
sure. All right, so we were. Okay. All right, so sometimes your calculator will present your answer with the exponent like this, like 1.32345 to the 8th power. Well, that's because the calculator, for whatever reason, that's the format they present your scientific notation, but it would be correct format. So you would need to convert that answer. Times 10 to the 8, okay? So that would be the correct format of put in scientific notation. So look at your calculator, look at the manual, and read about scientific notation. If you're not familiar with it, let me know, and we'll make sure you're familiar with it, okay? Because you will need it for calculations. All right. Which brings us to the final point of this, and this is called the percent, which I think you're familiar with this. This is, it's basically, it's a ratio. Specifically is the part over the whole. For example, hey, your grade, you take an exam, right? You got 100 questions. Let's say you got 80 of those 100 questions right. Well, the percentage is simply 80 over 100, where 80 is the part and the 100 is the whole, times 100 to give you the percentage, right? And then we can use that for any multiple things, not just your grades. So in this example here, we got a gold ring that has a total mass of 239.45 grams. Now, but it undergoes analysis for gold, and it has 198.38 grams of pure gold. So the question is, what is the percentage of gold in this ring? Well, we set the problem up as follows. 198.38 is the part. That's pure gold. Okay. And the 239.45 is the whole. We multiply it by 100, and obviously we're going to get this big giant number, 82.84819677, etc. Big number. You might be tempted to present that, but again, we got to keep track of our sig figs because we can't be more accurate than the least accurate numbers that we utilize. Here we divide them. So in this case, we think of sig figs, right? Not decimal places, but sig figs. And so we got 5 sig figs in the numerator, 5 sig figs in the denominator. That means that we need to have 5 sig figs in our answer. So we go to the 5 sig fig position, which would be right here, this 8. Okay, we look at the neighbor, which is 1, which tells us that the 8 remains an 8, and we get rid of the rest. Okay. And so our answer is 82.848% with the correct number of sig figs. Okay, and we can be that accurate because our numbers up here have spice sig figs. Okay. Any questions about that? Because congratulations, you are done with chapter 2. Now, what I want to do is share with you a couple of slides. I got them uploaded, and you take a look at them. One has to do with our metric system. Okay, we're going to use that quite a bit. And then the other one has to do with the technique that we're going to be utilizing in the next chapter to do conversions of one set of units to another. Now, we're going to use that technique not only for that, but down the road when we're doing chemical calculations, we're going to be using these techniques, and there has different names for it. But it's simply put, just keep track of your units, follow your units. But we'll have more of that here in a second. But anyway, we had talked earlier about what we use in metric system for mass, volume, and length as far as the units. In general, the majority unit that we use in mass is grams, denoted by the small lowercase g. Okay. Volume is denoted by the uppercase letter L for liters, and length is noted as a lowercase m for meters. Now, if we look at the three entities, mass, volume, and length, the nice thing about the metric system is they carry over regardless of mass, volume, and length. Totally different with the English units, a little more challenging. Well, anyway, we have that 1 kilogram consists of 1,000 grams. 1 kiloliter, with the K in front, consists of 1,000 liters. And 1 kilometer, 1 kilometer, consists of 1,000 meters. Okay. So the K represents a value, a greater value, okay, with respect to the smaller units of grams, liters, and meters, liters and meters. Now, when we start going down to smaller units for the gram, okay, first question I ask is, can anybody tell me how many years in a decade? How many years in a decade? Anybody know? Exactly, 10. Here's your hint right here, 10. Okay, here is again, 10 and 10. In 1 gram, there are 10 deciliters. Decade, deciliters, 10 deciliters. Okay, your unit's smaller than 1 gram. Stuck here.
I'm sorry, where's that chart at again that you're showing? Where's the metric conversion chart?
You don't see the screen?
Yeah, but I'm sorry, but in Canvas, just like open it up myself as well.
Yeah, this should be in Canvas.
Oh,
If not,
okay.
This it's a PDF file.
Oh,
Okay, and look in, forgot where I put it, but I'll double check to make sure you have it.
okay, thank you.
Sure, no problem. All right, and so we got in 1 gram, we got 10 deciliters. In 1 liter, there are 10 deciliters. Decigrams is what I meant. 1 liter, there are 10 deciliters, and 1 meter, there are 10 decimeters. Okay. Now, how many years in a century? 1 century gives us how many years? Exactly 100. Guess what? In 1 gram, there are 100 centigrams. And in 1 liter, there are 100 deciliters. And in 1 meter, there are 100 centimeters. Okay. And by chance, anybody know how many years in the millennium? Here, I'll give you a hint right there. In 1 millennium, okay, there's 1,000. So in 1 gram, there are 1,000 milligrams, a millennium milligrams. In 1 liter, there's 1,000 milli, short for millennium, 1,000. And in 1 meter, there are 1,000 millimeters. Okay. Now, the one you may not know is this one called micro. It's a symbol, looks like a U, and it's got a little lip up front. That's the Greek symbol for micro. There are 1,000,000 micrograms in 1 gram. There are 1,000,000 microliters in 1 liter. And there are 1,000,000 micrometers in 1 meter. Okay. For example, if you take vitamins like vitamin say E or D, you might find the symbol MC. What that is micrograms. So I know vitamin E, there's a bottle for 125 MC gem, or they have other units, they call it 5,000 units. I'm not sure what those are, but there's 5,000 of them. But that represents 125 mcg, which is 125 micrograms. Okay, FYI. All right, so all of these are conversion factors. Okay, and every conversion factor that I showed you here, there's 1, 2, 3, 4, 5. There's 15 conversion factors up here. All right, each one of them could be written as a ratio. For example, this one here, where we got 1,000 grams in the kilogram, could be written with kilograms up in the numerator, or alternatively, I can write kilograms in the denominator. Okay. Now you might be tempted, if I invert the 1,000 and change that to 10 to the -3. Don't do that. Just keep the number whole. Just flip it completely and just keep the number whole. Okay. You won't run into problems down the road. All right, so every one of this, so I said you got 15 conversion factors. Each one could be written as a ratio. So you have up here a total of 30 ratios that you can write. Now, granted, it is feasible to combine some of these, and that's not a problem, where I can combine liters to centiliters using this factor here. That's okay. But I would recommend not doing that until you're comfortable with using these factors. And then, if anything else, convert it so it works for you. Okay, so, for example, you may be asked a question, or could be asked a question, how many micrograms are in 0.125? Now, normally, I give you the answer here. Normally, what I would do is I would first write down what I'm given. Okay, kilograms, 0.125 kilograms. And then write down the units that I'm looking for. Okay, so this gives me a direction of where I need to go with respect to just keeping track of my units. Now, using those conversion factors up there, I need to find a factor that has grams and some other unit, kilograms, I should say, because I want it to read. So I got kilograms in the denominator. Why would I want to do that? Because I want to get rid of it when I multiply by this factor. Well, I know that there are 1,000 grams in 1 kilogram. And so with the first factor, I converted kilograms to grams. Okay. But I'm looking for micrograms. So obviously I need another factor here that relates kilograms in denominator. I'll cancel that out. And I know that there are 1,000,000 micrograms. So you see, I set that up, my units cancel, I end up with micrograms at the end. Now I just do the mathematics and there's my answer. And I kept track of my units. Now, if you're doing this technique, I guarantee you 99% if you keep track of units, you've got the problem set up. I can't say 100% because I don't control your calculator and the numbers that you push to get your answer. Okay, but I can help you with the units to set this properly. This technique is to allow us to go from apples to oranges. Okay. Now, we have 4 conversion factors, 3 conversion factors that are given to you. All those can be set up in any type of ratio. Okay. Quick review on your algebra. Remember, keeping track of units cancel out. That's just a quick review there. This file is on their website. If not, I'll definitely make sure I'll verify that it's up there. Then, of course, I got that image we had used before. Okay. Now, with that information, what I want to do very quickly, because we got 10 minutes left, is I want to demonstrate how, give me like 2 minutes for a second. I got to do something real quick. Something just popped up. 2 minutes. Okay. Sorry about that. All right, so this particular example, it's very quick and we'll be done here in a second, is I used this example back when I was teaching at Carrington College, teaching the dental hygiene students, and they also went through this conversion factors and so forth. So I created this crazy extreme dimensional analysis. Your book talks about the factor label method. In their book, they call it the dimensional analysis. It is nothing more than keeping track of your units. Trust me, you keep track of your units, you can go from apples to oranges as long as you got conversion factors in here. Okay. So I presented this example. I got where one dental hygiene student is equal to 6 grapes, 3.5 grapes is equal to 1 orange, 1 orange is equal to 6 toothbrushes, 3 toothbrushes equal to 1 banana. Pretty crazy, right? All right. So the question is this: given the following conversion factors, how many DH students equal 4.5 bananas? All right. Crazy. So we set that up. All right. Put up our first one. We got 4.5 bananas. Now, normally I would write way down here. I'm looking for DH students, okay, unit wise. And so that helps me set up my problem properly by looking at the factors that I have to work with and the units. So I start off with 4.5 bananas. So I look for a factor that's got bananas and I put bananas in the denominator, okay, because I want that to cancel. And that leaves me with 3 toothbrushes if I were to stop the calculations right here. Well, obviously I can't because I'm going to DH students. So I need one more factor. Okay. I know I need a couple factors actually. And I know from the conversion factors that 1 orange equals 6 toothbrushes. And I purposely put toothbrushes in the denominator. Notice I didn't do nothing to the numbers over here. I kept them as they are. So my toothbrushes cancel, bananas cancel. So at this point, if I were to stop the calculation, the units that I would be in will be in orange. Well, obviously, again, we're not at DH. So I need some more factors to get rid of orange and eventually get me to DH. Well, here we go. 3.5 grapes to an orange. orange in the denominator because they cancel out as I want them. Leaving me with the units of grapes. Getting close. I got one more factor here, and sure enough, with respect to the units, I am where I need to be. Because as I put my conversion factors in, I'm checking my units and make sure I set that up properly and that things cancel out. Okay? Things cancel out. So now, with respect to just the units, I am where I want to be. I'm set up properly. Now it's a matter of plugging in the numbers and do my calculation. When we start doing calculations down the road with chemical reactions, we're going to need at least 3 factors at the minimum, 3 factors. Okay. And when problems are asking you if there's a problem that says show work, this is what we're talking about. By showing how you got from point A to point B by showing your factors. All right, so finally, it's a matter of doing the math. Okay, and we end up with 1.3 DH students. So 4.5 bananas is equivalent to 1.3 DH students. Crazy, right? But the point of all this is these factors, these ratios that we have up here, you can set them up any way you need. And by keeping track of your units, you can set up your problems very well. Okay. And that's just a matter of plugging in the numbers in the calculator and you're good to go. All right. Perfect timing. Okay, well, enough of bananas and DH students and everything. But the point of all that is extreme, right? So it's a demonstration to explain to you that when you get down ready to do chemical equations, you're going to feel like, whoa, wait a minute. If I have 10 grams of potassium carbonate, how many grams of carbon dioxide am I going to make? And you might be sitting there like, whoa, this is apples and oranges. Well, think back to that extreme example. I can get from there to there with these conversion factors. And I will teach you how to do that, okay? And they're going to throw you out there on your own. At least not yet. All right, so